If I consider ionic compounds, means cations and anions will be there. Among them, whoever will be smaller can change the position as a part of defect. And to change the position, heat will be necessary. But that supplied heat will be compensated by increase in entropy in order the delta G value increases or delta G becomes more negative. To attain equilibrium, and one time equilibrium can be attained, and at that equilibrium the possibility of defect is there that we have studied. So one of the ion leaves the place and goes in some interstitial position, other gaps. That defect is called Frankel defect. Let us see it in detail. In 1926, Yakov Frankel noted a defect in silver chloride crystal. He found that small silver ions change the place and goes to interstitial position, causing vacancy at its original site. This effect later on labeled as Frankel defect. Let us see details of this defect. Here is an example of Frankel defect where cation shifts its position. It is called as cation-Frankel defect. Example is silver chloride crystal. By blue color, silver ions are represented and by red, chloride ions. Silver ions are smaller and they can move their position easily. So by white color, a vacant site of silver ion is represented because of its movement, and that moves in intermediate site. That was actually not the position of silver ion, but wherever gap that silver ion finds, there it goes, causing defect, causing abnormal or not regular arrangement. If I have to express this in terms of one reaction, then at bottom reaction is given. See, silver ion which was there at proper site. After Frankel defect, one vacant site gets created, that is of the silver. Plus silver ion goes in the interstitial position. Because of this, volume of crystal doesn't increase and mass of crystal also doesn't increase or decrease. Species are there, only among them rearrangement takes place. So this is a cation-Frankel defect. Not only for cation, for anion also Frankel defect is possible. I give you the example. This is one representative example of anion-Frankel defect. Fluoride kind of structure. This structure is shown by other crystals also. Here, anion, that's a fluoride ion, occupies tetrahedral sites, and that fluoride ion can change the position and can go in the interstitial site. So, such defect is anion-Frankel defect. Here it is not represented how fluoride ion is changing the position. Just for example, I am showing to you. I want to emphasize that Frankel defect is possible for anions also. One can wonder why crystal prefers to have a defect. Thermodynamics has an answer for that. If you study the variation of delta H value minus T delta S value and gives free energy change values, delta G values, you will understand the reason. Basically, to occur defect, heat is necessary. Delta H will be positive. But due to that, what happens? Entropy changes, entropy increases. So T delta S becomes more positive or minus T delta S becomes more negative. It is up to particular limit. After that, it is found that relative to the decrease in T delta S minus T delta S, increase in delta H is high. So there occurs one curve, there occurs one minima. So that minimum point of the graph of the curve of delta G is our equilibrium situation. It is a most favorable, most suitable situation. Because if we consider with no defect, then delta G value is relatively higher. With defect, little defect, such a way that there is a minimum for delta G, more stability, more negative delta G value, more favorable the situation is. If we increase the defect, then delta G value becomes little bit positive relative to the previous one. So most suitable thing is with defect, with dotted line. The number of defects are represented for that particular temperature. So for every temperature there remains a equilibrium situation where number of defects do occur. To make this concept clear, if you consider a water in a beaker, we consider water the liquid state, but there remains a vapors of water in a beaker at room temperature. As vapor and the water, as a gaseous state of water and the liquid state of water remains in equilibrium, likewise defects and perfect crystal remains in equilibrium. Defects are to occur naturally and they do occur. That's the secret of the defect. Of course, Frankel defect is one of the defect, so it also will occur. Necessity to occur the defect is the thermodynamic equilibrium, and thermodynamic equilibrium is represented in this reaction. Ag plus means regularly positioned Ag plus vacant site, vacant space at interstitial position, which is not the regular position, is an intermediate position, which remains in equilibrium to vacancy caused by migration of Ag plus. So vacant site of Ag plus migrated Ag plus in interstitial site. There remains a equilibrium, as like equilibrium remains between water liquid and water vapor. Here is a representation of total number of defects in a crystal by a formula. Small n is equal to capital N into e raised to minus delta H upon 2RT. Capital N is a total number of sites for that particular ion in crystal. Means in silver chloride, total number of Ag plus ion sites in the complete crystal. That's the value of capital N. Delta H is the enthalpy change during the defect. Defect occurrence is possible by absorption of heat. But because of that absorption, entropy is going to increase, therefore defects do occur that we have studied. So absorption of heat is an endothermic process. Then what do you think? When the speed of endothermic reaction will increase, when productivity of endothermic reaction will increase, yes, by absorption of heat. Therefore, at elevated temperature, therefore at high temperature, number of defects are more, following our simple Le-Chatelier principle. Here, capital R is a universal gas constant and capital T is absolute temperature. Important applications of defects are due to ion migration, due to conductivity. How actually the ions do migrate? What are the possible ways? Those are shown by the diagrams. In upper diagram by blue color, interstitial silver ion is considered. Means that is actually left its own site and came there in between the intermediate sites. And that silver ion will migrate to other site by two means. One, direct jump means from one intermediate site where already it is there to other intermediate site it will move. Other possibility is it will approach towards the nearest silver ion and nearest silver ion will approach to intermediate site. That's the interstitial C mechanism. So the ways of transfer of interstitial silver ion are explained here. As for any chemical reaction, there remains activation energy. Likewise, for this transfer also minimum energy is necessary. That's our activation energy. Therefore, I say it is an endothermic process. Absorption of heat and then the defects will be produced. To change the position from one place to other place, the ion goes through the different circumstances. the repulsions may possible. To overcome those all repulsions, some energy it should be with, and to have that energy, it absorb the energy from the surrounding. That we say as a heat absorbed for the defect. So I want to emphasize here energy of activation is necessary for defect also. Frankel defect is a defect where small ion, maybe cation or anion, change its own position and goes in interstitial sites. Let us know more about Frankel defect. During Frankel defect, there is no change in volume. There is no change in mass also. So density, what we consider as a mass upon volume, the ratio doesn't changes. Means density has no change during Frankel defect. This defect occurs for small ion. Means if I consider say for cation, the small cation means radius ratio should be low. Means for low coordination number compounds, especially this Frankel defect is observed. The examples are silver chloride, zinc sulfide. Few compounds are there, they show both defects, Frankel defect as well as Schottky defect. So silver bromide is one of the best example for that. Not only for cation this effect occurs, for anion also occurs, those who have the fluoride structure. The few examples of fluoride structures are calcium fluoride and strontium fluoride. They also do exhibit Frankel defect for but anionic Frankel defect. Previously, for photography, negative film was used, where a coating of silver bromide, silver iodide, silver salts was of importance. You will understand the role of Frankel defect here in photography if you know the actual concept of developing the photo. The coatings of silver bromide, when it gets exposed to the light, means flash, suddenly the reduction reaction was occurring, means Ag plus gets converted to Ag, and that Ag gets deposited on the film. After washing, Ag doesn't get removed, but Ag plus gets removed. Means wherever flash comes, wherever white light comes, the portion becomes black, and wherever that white light doesn't enter, the portion gets washed out, therefore becomes white. So negative film can be what develop. Mainly, as soon as light incidence on the film, the negative ion, say the bromide ion, gives electron, and that electron is taken by the silver ion. For that free silver ion, if they remain, then fastly reaction occurs. And where are free silver ion? Actually, free silver ion means which are not in the regular site, binded site. Free silver ions are in interstitial positions. And where is the interstitial position defect? It is a Frankel defect. Therefore, due to Frankel defect, due to increase in Frankel defect, good negative development was obtained. I hope you got the point, the importance of Frankel defect for the negative field. As a homework, simple question: can anionic Frankel defect be possible? Answer yes or no in comment box. Yes, in photography, how is the Frankel defect is important, you might have understood. Now let us see other defects, Schottky defect in next part.